You're right. We are live.
Okay, fine. I just wanted to make a very short introduction to the course. Now, most of the engineers have used or are using at the moment either a continuum description of the reality, and then they use finite element or finite volume or something like that, or use some discrete description with some particle method, or some of you both. However, the reality is neither of these. Both are approximations, and the reality is more like physical systems, and in my opinion also the space itself are chunks, collection of chunks, which are always finite. And so we started doing the, I'm not going to talk all the time.
You have to press it a few seconds. Okay, now it's
right. So, so we started developing this tool called Combinatorial Mesh Calculus in order to be able to do analysis on such collections of chunks, finite chunks, which are interacting through interfaces that are also finite chunks. And the description of these collections of finite chunks is called cell complex, or the descriptions are called cell complexes, and the Combinatorial Mesh Calculus was created to do analysis of cell complexes so that you can formulate physics of any sort. However, you know, usually taught in engineering, sometimes some of them in physics, but not in engineering. These are elements of algebra, topology, and geometry. And so the course will start with these elements and build up until it gets to Combinatorial Mesh Calculus in the second half, and applications. And Ian is a mathematician, and so he's going to be very rigorous, particularly definitions. Occasionally, I heard he's going to give a proof.
then one left to deliver.
Well, another thing, or less to deliver. And then it's, I would advise you to take notes because mathematics is learned when you write down. And I hope that after the course you will be able to do something with Combinatorial Mesh Calculus, potentially not immediately, like some of you are already doing. In the future, you're going to take it and use it for a particular problem that you have. Okay, thank you very much.
Let me just write some links. So this is the link to my project on GitHub. I will say about a moment. Yes, okay. So you can go to these things. This is a preprint of paper that is under review at the moment. And this is a software code. And this is a software code that was written mainly to model the problem that I saw there. And because it has some PDF file with some notes that I drafted, you can read it, it's very long, there's some mathematics there, examples. It's not very logical to follow, it's just what are my thoughts at the moment, but it can be a good supplement to this course. The notes that are there, it's for our website generated by different as well. Okay, and yeah, the main thing we want to do is be able to understand what this paper talks about. Before starting with algebra, I want to just start with a little bit of logic notation set theory like that, in order for everybody to be on the same page. So first of all, in order for everybody to be on the same page. So first of all, let me introduce some notation. Just to be everybody to be on the same page. So oh, I will denote by either integers, which for them we will put 0, and so on. So that time, the positive integer, the natural numbers. So that are the integers, 0, plus minus 1, and so on. Here are the rational numbers. Here with this sign, okay. I will also use positive numbers, for example, and that plus are the positive integers, and so on. Of course, Q plus and R plus are positive rational and positive numbers. I assume everybody is familiar with self-building notations. For example, if I have some property phi, so phi is property, and A is a set, I can take the subset of, so B is OX in A, such that f of x is true. I will not write this true, but it is not important. Everybody fine with that set build notation? Okay, for example, I can write the positive rational numbers like Q plus. These are all rationals such that Q is bigger than 0. Okay. Yeah, for a set Z, no, if x is a set, then of course, and then it's integer, x prime is the x to the power and the pairs. So x1, x2, x0, x row. If I want to. Also, I can have matrices. They're usually matrices are not interesting only as tables, but when they have some algebraic structures, we can add matrices multiply. But if m and n are integers, I will denote by n y matrix with n rows and n columns of x. These are x11, x and n, where x is g using x. Anything unclear for now? Okay. Uh, so in mathematics, we form a lot of complex formulas. And we have a language to do that, the language of logic. So if we have formulas, we can, okay, so formula is something like that, some statement, x bigger than 0. And they can be made more complex. If we have, so formulas. So if P and C are formulas, we can do the following operations with them. We can do the negation of P. So this is the sign for negation. Usually there are brackets on the outside, so when you do complex formulas, you know how to read them. Like when you have expressions with numbers. But when it's simple, we can skip them. I will put brackets when necessary. So this is negation. So it's the opposite of P. We have conjunction. So it is there are different signs for conjunction. I will use this one, which this is conjunction. So it's logical and. We have disjunction. If both are true, it's fine. Because the language when we say I do this or that, some people assume it can be both. So it's disjunction. We have implication. So if F is true, then C is true. Oh, okay. So the conjunction is true when both are true. The disjunction is true when this one of them is true. For implication, if this is false, everything falls from false statement. If this is true, then that should also be true. We have equivalence. This is just in both sides. Equivalence. Okay, this for now is just so-called propositional logic, but things become harder when you include quantifiers as well. So if x is some variable, so x is a variable, we can form the universal. So for all x, this is universal. So for all x, this is universal. And how do we prove that something is true for all x? We take some arbitrary x and prove that the statement is satisfied. And we also have existential. So instead of just saying follow and blah blah and use long words, I can write quantifiers. There are a lot of rules, but I will not talk about them right now. I want to ask you if are there people that see these symbols for the first time? Okay, then you should tell me what this means. So let's say we have E, this and real quiz, let's say we have E, this and real interval. And f is a function from this. Uh, this is just for exercise. I will not talk about this piece.
May I ask something?
Yes.
Can anybody interrupt you to ask questions?
Yes, of course. Oh, if you ask questions, you take the microphone. Yeah. Oh, if you just have something very little to say, don't use the microphone. If you just some symbol like that, but if you have some meaningful question, you have to take them. It's better to take the microphone. So the recording shows. Uh, in the recording, everybody can. Stay there. Okay, we'll start here on the left. Can you tell me what this means and what this means? So, can you give him the microphone? Is it started? It has to be green. Okay.
The bottom one is connectives. We need to explain what it means.
Now what is?
For all x within the interval, all epsilon larger than 0, it's delta larger than 0, such that for all I in the interval, given that x and y are a distance of less than delta, implies
Okay, what's this?
implies.
Yeah, but what this formula says in regular language?
This is provided.
No. What's the definition? What's the definition? I write a definition for some very well-known property.
Just say, like, if you get 2 points of function and you sort of really put together.
Yeah, but what's the name of this thing?
Continuity.
Okay, and what's this?
This one is also continuity.
But can you tell the difference?
Between.
Sorry? For all epsilon bigger than 0, there exists delta bigger than 0, so that for all x and y in the interval, if the distance delta, then the values of f are distance epsilon. What's this? So This is called uniform continuity. Yeah. Has anybody heard of uniform continuity?
Of a uniform convergence.
Well, it's close. I will not talk about calculus at all. I just wanted to illustrate how formulas are formed and can you read them. And okay, this is called continuity. So this says that the function f is continuous in the interval I. So the function f is continuous in the interval I. This is the definition of continuity in analysis. So f is continuous. And this thing says that f is uniformly continuous. Okay, if you see, look at the formula from here, they are the same, but they start different. Here we say we have for all and then exist, but here we have for all exist and then again for all. Can you tell me which one of them is stronger than the other? For a simpler example, if we have for all x exists y such that something is true, and exist y such that for all x something is true, which is stronger?
The uniform.
Y such that for all x something is true, which is stronger?
The uniform. It doesn't depend on the side.
Yeah. So every time when you have existence before universal quantification is stronger. So, for example, if x and y are denote people, and I say for any person there exists persons that two of them get along. Maybe this is true, but this says for there exists a person says that all other persons get along with this person. Okay. So nobody will study logic. Well, we won't do much logic, but we have to do some arguments, some deductions when we show something. So that's why I'm talking about that. Okay, so this is stronger. And so here we have the existence is at the end, here is in the middle. So uniform continuity is stronger than continuity in general. Stronger than. Okay, let me just finish with the set notation. So if we have E and B are sets, we can form the section, which is all the B are sets. We can form the section, which is all the A and this is another symbol for conjunction, but I will skip it. And that belongs to B. The union is conjunction, so it belongs to at least one of them. So it belongs to this or that. set difference. So okay, I will like no. Yes. So these are the elements that belong to A but don't belong to B, and X doesn't belong. And these are usually shown in like then by and the difference this one here. Okay. So let me set which. The Boolean, this is the set of all subsets. So this is so this is set of such set Boolean or power set. It's called Boolean because power set because it has to the power of elements. Yeah, sometimes it's not also. So this is our limitation. Why is that? Well, if you have, for example, sets with two elements, what are the subsets of A? What are the subsets of two element set?
The empty set,
Okay. Empty set.
the set which is 0, the set which is 1, and A itself.
Yes. Okay. Okay. Well, we will need the Boolean set when we talk about exterior. We will need the Boolean set when we talk about exterior algebra because the basis of exterior algebra will be formed by all such kind of combinations. So if A is finite, then the Boolean of A has 2 to the power of 8 elements. Okay, so by absolute value I mean the number of elements in a finite set. This is the empty set with no elements. So, and yes. And so another operation is, so if we have A and B sets, A belongs to A and B small belongs to B big, we can form the order pair. And pairs are defined in such a way that if A prime and B prime are so what's the definition for pair order pairs to be equal? So A equals A prime and B equals B prime. So if and only if A equals A prime and B equals B prime. Okay, for all the pairs, A times B is the set of all pairs. A, B, where A belongs to A, and B belongs to B. This Cartesian product, if we have, for example, A, B, 0, 1, 2, we have A 0, A 1, so 0, 1, 1. So it's A equals 0, 1, 2, and this is the A times B. And it is denoted by product because number of elements is the product of the number of elements in each sets. So if A equals n, the number of elements in P is n, then A times the number of elements A times B is A times n. Okay. Um, okay, let's now talk about functions. Here I will pay more attention to functions because we use them a lot. So if let x and y be sets, this is informal definition, but if a function from x to y, also denoted by, or also can be written as x, from maps, f maps x to y. This is good when you do diagrams. Is a function I for which x with which s of f of x small of x big corresponds to unique y equals set of x with y, given by some illusion. Okay. So this was not very rigorous definition, that's why I didn't write this definition. Now let's write some rigorous definition. Okay, now, so we start with three sets. And f is function from x to y, and g is function from y to z. What can we do with that?
Composition.
Yeah. So we define J after F or J composition with F. This small circle is used. This function from X to Y. How? By as follows. So J. Oh, sorry. So J of F or composition. So this is a new function between these sets, and it's defined by J of F of X. So we go from X to Y in big Y and go to Z in big Z. It can also be written as follows, but diagram, or in a diagram, it can be written this way. So X, F, then we go to Z, G, and G, and do you know how such kind of diagram is called? So yeah, this is called a connectives diagram, where you have diagrams of functions, and no matter how do you go, you get the same result. So you start from X, go to Y, and then to Z, and the other way is directly by the composition. Let me give an example of composition.
This is the definition of category if you replace X and Y with quantities.
Like this,
And F and G with I.
yeah. We don't do that. Okay, so if we have some, like, for example, set X equals, it has three elements. A, B, and C. Y has three elements. Oh, no, 0 and 1, and Z has 4 elements. W, X, Y, Z. And we have the following function. So we have A, B, C. Here we have 0, 1. And W, X, Y, Z. So function maps everything from here to here in some way. So for example, let's map A to 0, B to 1, and C to 1, and then map 0 to X and 1 to Y. So this is F, this is Z. So what we will have is G composed by B. This is Z. So what we will have is G composed by B. How what's the diagram for G composed? So this is the diagram for a function. It has from maps 3 values to 2 values, and it maps A to 0, B and C to 1. And here the 2 values in Y are mapped 0 to X and 1 goes to Y. What's the diagram of the composition?
With A to B, not directly onto X to B to C.
Yeah, so A, so we have to have all of things here. We don't skip anything. So A goes to X, B goes to, and C goes to. Yeah, so this is composition. Okay. Let me give let me give the definition of equality function. So, I didn't talk about equality of sets. So, if in fact an axiom of set theory, let x and y be sets. This is called axiom of equality. Then x equals. Can you tell me how do you check that two sets are equal? Can you be more precise? No, it has to be subsets of one another. If and only if. Do you know this simple if?
Only.
Does anybody know this symbol?
Only.
Does anybody know this symbol? Okay, this means if and only if. So it is in both directions. So x equals y, then this thing I will say is true, and the other direction as well. If x is subset of y and y is subset of x. Okay, I didn't say what is a subset. How do we define by a formula what a subset? Okay, can somebody tell me in natural language what does mean some set to be a subset of another?
So in this case, it's for every x with a certain px, x is an element.
Yes. Yeah, I will write it was correct, but I will write it this way. For any variable f, I will write it this way. For any variable f, x small if x is x big then it is in y. This is this part here, and so we have to make a conjunction that is here and to swap for all x is in y, and implies that x small is in x. This quantifier and this quantifier are totally different. These are two separate formulas, although they use the same variable. I can make this thing a, it won't change. Okay. I should have said this before, but anyway. So this axiom is used when you want to prove that two sets are equal. You prove that first one is subset of the other one, and then the reverse. Maybe we can. Okay, let me do something very fast. So example A intersection with B equals B intersection with A. So how do we prove this? Sorry? No. Formally. So we have to prove that this is a subset of this and another direction. And because it's symmetric, I will show only the one direction. Okay, so let x belong to A intersection with. What does mean for an element to be of in an intersection.
This belongs to
X belongs to A and X belongs to B. Well, by definition, this means that it belongs to intersection because this is like a statement in the language and we can swap the order. So this means that, so hence X belongs to B times B intersection of A. Because what it says that it should belong to B and belongs to A, but look at that. Only the order in the language is different. So therefore, X belongs to therefore, so X was arbitrary, so this means that A the intersection of A and B is the supported B intersection. A similarly, the opposite direction. Okay. So I wanted to talk about equality functions, and I just forgot that I didn't talk about equality sets, but now we move to functions. So let X and Y be sets. F and so if we go, if you do the identity of X and then do F, so identity of X goes from X to X and then we go from X to Y. This is the same as going to the other direction. Identity of Y composed with F, which is the same as F, which is the same as F. And the proof, how do I proceed for the proof? Yeah, when I want to show that two functions, so this is functions from X to Y, this is a function from X to Y, and this is a function from X to Y. Okay, let me write it better now. So we have X, identity X, it's X, we have Y here, this is F, and this is F as well. Let's prove that. Andre had suggestion, but nobody listened.
Just show it how you can go and what's not.
Yeah, okay, let me say A and X is arbitrary. Okay, this is arbitrary. Yes. Then, okay, F identity of X applies to A by definition is F of identity of X applied to A. I use the outer bracket but only the internal one. And so what is the identity of X at A? It's A. So we can F of A. Similarly, identity of Y F of This, what is this? We need to expand this. Okay. And we have identity, so you only need this one. And FFA, of course, is FFA. This is FFA. So all three of them are the same. Nice. Okay. Let's have some break. Maybe to 05. So, some break. It's 2:04. When we continue. 4 no past 4:02 to 4:02. 4 no past 4:02 to 4:02. Let's continue at 5:02. Okay. Let's finish this recording and start another one. Oh, I ended
When I
it.
studied English as a child, there was